Yes, it is now. Hey, my name's Tim. I'm a PhD student from the University of Sydney, and I'm kind of the lead developer for all the NCSS challenge related stuff. And this talk is going to be kind of split into 3 discrete sections, if I have enough time. The first section will be on the technical side of the challenge and what kind of stuff we need to consider when doing any kind of online programming stuff. The second section will be on what our application stack is, for those who are interested. And the third section, if I get time, will be on both TryPython and Gumby App, which Georgina and Katie mentioned in the previous talk. So what is the NCSS Challenge? The NCSS Challenge is a programming competition for high school students in which we aim to teach programming via problem-based learning. We have students from years 5 through year 12 in Australia, and a couple of students from New Zealand in the mix as well. It runs for 5 weeks, and the last couple of years we've grown greatly in numbers. So this year we had 2,071 students, up from 1,391 last year, and enrollments are greater than students because students can enroll in multiple courses per year. So the enrollments, you can see, have jumped up quite a bit from just 3 years ago, from 489 up to 2,400 this year. So it's still growing by quite a large number. And each week they get a set of problems that they can attempt. Quick live demos is always going to be dangerous. This is the challenge site. It's got a nice, pretty Ajax-y site. Each week, this is the beginner's Python course that we run, that's currently running this year. Each week, students get a set of problems. In beginners, you get 10 problems per week. And this is the Hello World problem that Katie and Georgina mentioned in the previous talk. You get a problem description up the top, and you get some code. So print hello world. And this will die, so we say check answer. Down the bottom, your solution failed at automatic testing. This is your code. Blah, blah, blah. You're missing punctuation, yada, yada, yada. Fix up the tests, and you'll eventually pass. Yay, you passed all the test cases. Green arrows. And this problem then is marked as green, and you're good to go. And so each week, students get a set of problems, and each of the problems have a set of test cases associated with them, and to be able to pass the problem, they need to pass all the test cases. Standard problem-based learning approach. So that's the challenge itself in a very brief nutshell. So what we actually require then, what do we actually require from the challenge side to be able to support such an infrastructure? So we need to allow students to submit arbitrary code to be then run on our servers. Warning bells. Danger, Will Robinson, this is not good. From the university's point of view, so the challenge site itself, the challenge infrastructure, is used within the university to teach a number of courses. It's not just used for the NCSS challenge. So the university had some additional requirements that we needed to put on this infrastructure. So not only did it need to support Python, it needs to support any language, quote unquote, which makes the problem infinitely more difficult. You support a large number of concurrent users and allow for the standard admin stuff that a university course would require. System usage this year. Within the university, it's been used for 3 courses. In semester 1, in Info 1903, we taught Python, Bash, and MySQL via the challenge site. We taught NJ201 to 700 students using MATLAB, or Octave, in fact. There's a specific clause in the MATLAB terms and agreements that says you cannot use MATLAB for an online system. So we can't use MATLAB. Info 2120 for Postgres, which is 300 students, and the challenge, which is currently running, where we have 4 courses. We have 3 versions of Python, beginners, intermediate, and advanced, and then Arduino programming, which is kind of embedded C. So, executing arbitrary code. Bad. The testing framework needs to allow arbitrary code execution. So what do we need to restrict on our servers? Do we bother restricting? Who would want to do anything evil on our servers? How could we do this? We could do some kind of virtual machine magic. Maybe. Virtual machines are kind of a large solution though. When you're running, say, 40 test cases a second, a peak, firing up 40 VMs is not a particularly nice solution. So I went and looked through the challenge site this morning and grabbed some submissions from the last week of what's gone through the challenge site. So there's 3 here. The file name on Filesystem that your code gets put in is called submission.py. So this first one is doing an infinite fork bomb on yourself. The second one is trying to delete stuff. The third one is trying to spam the New South Wales Department of Education via email. The top one there, we're trying to flood our RAM. Then another fork bomb. Then we're trying to walk up the code stack using the inspect framework and code frames in Python. We have this other quite neat one, which has nothing to do with decoding UTF-8, as the function would suggest, which is trying to extract the source code from upper wrappers that we have. So, no one would ever do anything evil. So, obviously we do need to protect some stuff. So how and what do we need to protect? So, presumably we need to do some kind of time limitation, but then the question comes, what do we define as time? Do we define it as wall space time, user space time, kernel space time, both? Do we need to limit somehow the amount of memory? And again, what do we mean by memory? Do we mean physical, virtual, shared? Presumably we want some kind of process limitation. And then fun question for the audience, how many processes does the Sun JVM fork upon invocation? Way too many is the answer. It's like 32. File system writing. Presumably some questions you actually may want to test people's ability to read and write from files. So how do you sandbox that in some nice manner? Network access. Presumably you don't want any network access. Maybe you do, but presumably you don't. And this is just a very small subset of the things you need to consider when restricting people's code if it's arbitrary code running on your own servers. So, Linux to the rescue. Linux supports the ability to limit all of these aspects out of the box, if you know how. So what tools do we have in our inventory? We have the useful rlimit call, which you may have heard of, which does user space CPU limitation. We also then have data segment limitation in RAM, and we can put limitations on the number of processes. We have signals then for doing time-based killing. We have IP tables for network, and most importantly, chroot. And if you've ever heard of chroot, it's probably a good thing. It allows you to do magic. So what is chroot? If you've done any kind of Linux or work in Linux before, you should be used to the idea that you should be able to do anything. You're a sensible person, you're running Linux, you can do whatever the hell you want. So the question then is, what makes / the root file system? / is just some pointer to some location on disk. So the question then comes, can I change where this magical / points to on disk? And just arbitrarily bind where / gets pointed to? And the answer is yes. This is what chroot essentially lets you do. So we can create inside our overall Linux box, we can say, create a new Linux image inside there, somewhere on disk, like dev sda1 / foobar, and read chroot into that. So, for example, ls/, we have a whole bunch of stuff. ls/workers/jail, we have another full Linux instance set up in this particular directory. We can then chroot into there, and any programs that are run in there, their / points to the outer level of workers jail. Spelt American for some reason, instead of Australian. Whoops. And to bootstrap, if anyone's ever heard of this, is a funky little Unix tool which lets you bootstrap Debian distros via package management. So you just specify a list of packages you want to install in a particular location, and that will install them in there for you. It's quite neat. And because it's package managed, we can easily maintain this in a distro. We just run aptitude over the particular directory, and we can keep packages up to date nice and easily. So how does this work? So we have / workers. We have these worker daemons. Worker daemons are going to listen to submissions from the challenge website, and when the submission comes in, the next daemon that's free will grab the submission and execute it and send back the result. So workers/jail is where we have this bootstrap jail that exists. This Linux distro inside the outermost Linux distro. We then fork and chroot into the jail. So the red / there is the file system that the user's code then sees. And then we have the resource limiter that goes on there. So it puts on the time restrictions, the memory restrictions, the process limitations, the network restrictions, all those kinds of things. We then create, each daemon has a unique UID and GUID with no read and write permissions to anywhere apart from /temp/random, or $random I should say. And then the user's code is then exec into /temp/random, or that particular random directory. So this setup works well for everything apart from file system restrictions. So file system restrictions thus far, we've given the user full read and write permission to their current directory there, which is /temp/some random value. So the question then comes, how do we sanely prevent people from, say, just flooding our disk with random data, or trying to put a high load on our disks? iLimit doesn't provide a good way to do this. And a lot of the questions that we do, we often want to catch people's I/O mistakes and give them back some kind of meaningful feedback. For example, if they never actually do a read call and the problem is all about reading from files, it'd be a much more meaningful error message to give back to say you never actually read from the disk than to say your program failed. Yes? So the question was, how do we sanely put on file system restrictions and give meaningful feedback to the users at the same time? And this is where Fuse comes to the rescue. So you've never heard of Fuse before. Fuse is a tool that lets you write your own file systems, if you so desire. It stands for File System User Space. And so what we did, I wrote my own file system. And the user's code then, this temp/random value, is actually my own file system. So I get every I/O call that the user makes. And from that, I can determine whether or not the user is doing something stupid, and we can go from there. So this picture that was from before now gets slightly more complicated. For every test case that's run, this challenge FS, this special file system, gets invoked in /temp/random, and the user's code gets invoked in there. And then we get to monitor every single I/O call the user makes. Then we have multiple workers per physical machine, and then we have multiple physical machines. This process then all scales out. And that's, in a nutshell, how we restrict code. I'm sure there'll be some questions about that afterwards. Next point. So the application stack then. So this challenge site is pretty Ajax-y thing. Whoopsie. At peak time, has to support about a user load of about 2,000 or 3,000 people currently. So how do we do this? So we have a number of Python technologies in our application stack. We run Django. We have South on top of that for doing migrations. We do Fabric for deploying to servers. VirtualEnv for easy package management. And we use Pigments for syntax highlighting. The overall system then. That's a crappy slide. We have lots of Ajax and JavaScript. And one thing that's kind of neat, I guess, about the site is that the entire site is built client-side. So no HTML is ever generated on the server side. The entire site is built in JavaScript. And that's to move all the workload from the server to the client side. The only real downside about doing this is that it makes it a lot more annoying to debug, because you have browsers like IE, which don't give you any kind of decent JavaScript feedback for debugging. And the other thing that we found when doing a lot of quite heavy Ajax-y stuff with quite large data segments was that browsers are not particularly good at handling large chunks of JSON. If you send back a 2 meg JSON object, your browser will die very badly. It will sit there churning for about 12 seconds trying to parse this thing. We have Postgres running in the background, Postgres replication, and we use Whiskey over Django and Memcache. So we then have an application stack that looks somewhat like this. So then we have a complete segregation of the web front end to the actual workers. So we have this set of web servers that will serve the web requests, and this set of servers that will actually do the execution of the code that people submit. And so we need some way to get the messages or get the code from the UI that the user submits in Django to the workers in the background. And to do that, we use AMQP, which stands for Advanced Message Queuing Protocol, something like that. It's a standard protocol, and the AMQP server we use is called RabbitMQ, which is a messaging queue that's written in Erlang. And it works very well. If you don't do any kind of generic message passing of data of key value pairs, AMQP works quite well. And so then we have, picture extends a bit like this. So now we have that the user's code goes from Django to the AMQP cloud. The workers then pick it up. They process that particular submission, send back the results. Then the results statement talks to the database. And so we have a nice complete segregation between actual place where the user's code gets executed and any kind of meaningful information, such as the database. Yeah. And then briefly, the third segment of this talk is talking about technical issues with high schools that we have to deal with within the challenge. So typically, high schools are quite restrictive on what they can install on their machines and what machines they have even. And that's both for political and technical reasons. And as it was mentioned in the previous talk, high school computing teachers, I should say, are often not programmers. And so then trying to interact with teachers while we're trying to teach them and their kids to program is not necessarily easy, because you're also sometimes trying to teach the teachers who are then trying to teach the students. The biggest issue we've had recently, as again was mentioned in the previous talk, was the New South Wales Department of Education laptops, which are very, very restrictive in what they can do. So they're a cut down or restricted version of Windows where you cannot run any exe that's not in C Windows. There's no CD drive, and this includes removable media. You can't put in a USB key and run an exe that's on that. So things like portable Python won't work. Python's not installed. The only thing that is installed really is Photoshop, Word, IE8, and Silverlight. So this is a pretty small subset of things to try and work with to try and get people to actually use Python. So we had then 2 attempts to try and actually get Python onto these laptops. The first attempt was this TryPython thing. So if you have a laptop, and you can try and go to it. TryPython is, myself and James Curran modified the existing version, which is on trypython.org, to work better for the actual challenge site. Actually, I can do it now. Maybe. Yes. TryPython is written in Silverlight. Maybe. No. Let's ignore that. Written Silverlight, runs on IPython, and because because the DT laptops that already have Silverlight installed, this will work. And we've found that it's actually reasonably popular even for people who have Python installed already. It's quick and nice and easy to just pop up another browser tab and have a fully working Python interpreter and a text editor in another tab than it is to sometimes open another app. So you should have a look at that at some point if you're interested in that. The second attempt that we had was what we called Gumby. And this is a very cool project that a person from Mozilla brought out. I forget his name, but the project itself is called Emscriptum. Has anyone actually heard of this? Awesome. Apart from the people I've actually shown. Emscriptum is a funky little tool that will let you take any C program and compile it to LLVM. Sorry, let me rephrase that. It takes LLVM bytecode and compiles it to JavaScript. And the consequence of this is any program you can convert to LLVM bytecode, you can then convert to JavaScript. So what we did, what Ben Taylor and myself did for Gumby App, was we took the CPython interpreter, compiled it to LLVM bytecode, then compiled that to JavaScript. And so the consequence of this is you have a fully working CPython interpreter in the browser. Now let's see if this one will work any better. Apart from not being centered, that actually worked. Aha, sweet. So this is Gumby App. It works horribly in IE because it's a 2.8 meg JavaScript file. Unsurprisingly. It works all right in Chrome and Firefox and Safari. So for example, We can run this, and down the bottom we can see here is the output. And this is actually running in your browser on the C Python interpreter. This is not firing off some web request, nor is it actually doing some hackery or some really small subset of Python re-implemented in JavaScript. This is the actual C Python interpreter with a couple of wrappers in there, which is quite funky, I thought, anyway. Have a play with it. It's forkable on GitHub. I haven't had time to work on it in quite a while, so feel free to have a go. Yes, and it uses Emscriptum and the Clojure compiler from Google. And yes, that's me done. Thank you.